When we're sending data from one computer system to another over a serial link with a simple clock and data protocol like this, I've showed you in previous videos how it's pretty straightforward to build a circuit that computes the parity bit. So we just have our clock and data coming in here, and we just have an XOR gate and a D flip-flop, and out the other side comes a parity bit that we can use to validate that our message was received correctly, or at least that certain types of errors didn't occur when we received our message. But of course, a parity bit is not very robust. There's all sorts of errors that might be injected into our message that a parity bit won't catch. And it's actually pretty easy to inject an error like that, and you'll see the parity bit is still matching on both sides, and so we haven't actually caught this error with the parity bit. So in other videos, I showed you things like checksums and CRCs that are much better at catching all sorts of different types of common errors that might occur in a communication network like this. But the downside of those is that they're much more complex. So CRC, as we saw in the last video, the math behind that's fairly involved. So we take our message, we convert it to a polynomial. We then divide that polynomial by this generator polynomial that we come up with, and then that division, after we do all that long division, that results in a remainder, and then we subtract that remainder from our original message, and we get the actual polynomial, the message that we're going to transmit, and then we can use the mathematical fact that transmitted message is a multiple of our generator, and the receiver can kind of do the math on the other side to determine if any errors occurred. Now that's a lot more complex than our simple little parity bit here. But what I want to do in this video is actually look at the math in a little bit more detail and look for some patterns that exist in this math that we're doing to calculate the CRC, and show how we can use the patterns that are in here to actually distill this fairly intimidating looking computation into reasonably straightforward hardware. So let's take a closer look at this process of computing the CRC and see what sort of patterns we can find. So it all starts with the message that we want to send. And so this here is the message we want to send, and it's if we chunk this up into little 8-bit chunks, we've got an H there. That's the ASCII for an H, or the binary representation of the ASCII value for an H. That's an I. And then here we have an exclamation point. So it's HI exclamation point, hi is our message, followed by 16 zeros. And these 16 zeros is where we're going to put our 16-bit CRC. And that 16-bit CRC comes from this hairy little division problem that we've got here. And it comes from the remainder of that division problem. So once we've done this whole division problem, we end up with the remainder. Those 16 bits are the ones that we fill in here to complete our message plus CRC. But this whole division problem starts with the message itself, because the polynomial that we start with here that we're dividing is based on our message. So each time we have a 1 in our message here, we have a term in our polynomial. And each time we have a 0 in our message, the term is not in our polynomial. And so that's what we start with. And so how do we get from this polynomial that we start with that represents our message down to this 16-bit value that is our CRC? So how does this process actually work? Well, it looks like we're doing a bunch of subtraction. So each step along here, we're subtracting something. So we start with this thing representing our message, and then we subtract something, and then we get something, and then we subtract something else from that, and we subtract something else from that. And we just keep doing this subtraction until we ultimately end up with our CRC. So what is it that we're subtracting? Well, it's all multiples of the generator polynomial, right? Because the way that we come up with what thing to subtract is based on the process of this long division that we're doing. The first term here, we say, well, how many times does x to the 16 go into x to the 38? It goes x to the 22nd times. And then we take x to the 22nd and we multiply it by the generator polynomial, and that's what we subtract. So another way to think of that is, if our generator polynomial is this x to the 16 plus x to the 12 plus x to the 5th plus 1, and we can line that up with the columns here, but then we multiply this generator polynomial by x to the 22nd, which has the effect of essentially moving it 22 places over to the left like this. And so what we end up subtracting is a multiple of the generator polynomial. And when we subtract, because we're using this finite field, the result is that essentially what happens is each of these places where I've drawn these arrows, essentially each of these places that lines up with the terms in our generator polynomial, we flip the bit value there. So if we have an x to the 38 here, we flip that and we don't have it here. So here the x to the 34 term is not there, and now it is. We flip that. Here x27 is there. We flip it, and now it's not there. And x to the 22nd is not there, and we flip it, and it is. The rest of the terms stay the same. So here, these terms aren't there, and so they're not here down here. X to the 30 plus x to the 29 are there. They remain down here. So we're only flipping these 4 terms. Then what we do is essentially, if you think of this sort of mechanically, what's going on is you just slide this over until this x to the 16 arrow lines up with another term, in this case x to the 35, and then you flip those bits, and you end up with this polynomial down here. So we just flipped those 4 positions from this line here. So this x to the 35 got flipped off, this x to the 31 got flipped on, and so forth for each of these two. And then everything else just stays the same. And then we just slide over to the right, flip those 4 bits, and we end up with a new polynomial here. And then we can slide over to the right, keep sliding until this x to the 16 lines up with a term, and then flip those bits. And we end up with another polynomial. And we just keep doing this, sliding, flipping those bits, sliding, flipping those bits, sliding, flipping, and we just keep sliding and flipping those bits until ultimately we eventually get to the point where we slide over, and now x to the 16 lines up with the x to the 16 place. So we've slid essentially as far over as we can. So we've gotten all the way to the end, and then we do that final flip, and this polynomial now that we end up at the bottom there, that's our CRC. So as messy and as complicated as this math might seem, it's actually a fairly simple algorithm to get from our message down to our CRC, of just lining this up here and then sliding over and flipping and sliding and flipping. And we just keep doing that. We'll ultimately end up with our CRC. So now let me show you that same mechanics of sliding and flipping represented a little bit differently. So here we have our message in binary, and then this is the generator polynomial. And another way we can think of it with that same sliding and flipping sort of idea is we can slide our message along like this until the x to the 16th place lines up with a 1. And so we sort of keep sliding and sliding and sliding. And so here we have a 0, and now it lines up with a 1. It's like, okay, now that that lines up with a 1, what we can do is we can flip each of those 4 bit positions. So what I'll do is we'll use a little whiteout here to flip each of those. So that becomes a 0, this becomes a 1, this becomes a 0, and this becomes a 1. And now that we do that, we can keep sliding. So now we just keep sliding this until the x to the 16 position lines up with a 1. And there it goes, it lines up with another 1. And so now what we'll do is we'll flip those same 4 bits again. And now that we flip those 4 bits, we'll slide again. And now this x to the 16 lines up with another 1, so we'll flip those 4 bits again. And then we keep going. So slide over, that's still a 0, slide over, that's still a 0, slide over, and now we've got a 1 here, so we'll flip those 4 bits again. And hopefully you see this is a pretty straightforward pattern. So we can just continue to do this slide over until the x to the 16 place lines up with a 1, and then flip those 4 bits and keep sliding and flipping until we finally get to the end. And then we'll slide again, and now this lines up. And at this point, we're now at the end, so we'll do one last flip. And now that we're at the end, we've done that last flip, you'll notice that all of the positions from x to the 16 to the left have all been zeroed out, so that's one sort of property of this operation. And then the last 16 bits should be our CRC. So let's compare that to our long division here, and hopefully, if I did this right, yes, it looks like it's the same, doesn't it, right? So that's our CRC. And we're able to calculate it just by this sliding and conditionally flipping these 4 bits. And so those are fairly mechanical things that we ought to be able to do in hardware. And so when I think about that idea of sliding bits along, what comes to mind for me is something like a shift register. And so this is a 16-bit shift register. It's just made with a bunch of D flip-flops all chained together. And basically the way this would work is if we've got our data and clock over here, we can imagine our data coming in like this. And if we have a data bit, let's say we have a 0 here, when the clock pulses, that 0 will be read into that first D flip-flop. Then the next time the clock pulses, if we have a 1 here at the data input, then that 1 will get read into that D flip-flop, but also the 0 that was in the first D flip-flop gets read into the next D flip-flop, because all these clocks are chained together or are connected together. And so with each pulse of the clock, each new data bit will get read into the first D flip-flop here, but then each subsequent data bit just shifts along down this shift register. And so this gives us something very much like that sliding that we're seeing as part of our CRC algorithm. So it seems like this would be a good place to start, is with a 16-bit shift register like this that we can read all of our data into. And then once we get this working, we can start to think about, okay, how would we flip certain of these bits under certain conditions? So we've got our transmitter here, and if we reset this, we can see we've already got the clock and data signals all set up here for our transmitter. And so those are going to be the inputs to our shift register. So we've already got that. We've got a clock that's pulsing every time there's a bit, and we've got a bit that's either on or off, indicating whether it's a 0 or a 1. So we're going to have no problem as far as getting the inputs to our shift register. We just need to build the actual shift register. And to do that, we can use the 74HC273, which has 8 of these D flip-flops in here. So we're going to need 16 of them, so we'll need 2 of these chips. But each of these little blocks in here is one of these blocks in our shift register, and we can just hook them up like I've got here. And actually, I've already got one of those 74HC273s here that we used because we did use one D flip-flop for our parity circuit, so we can actually reuse that. So let me actually get rid of some of the parts here for our parity, and we can reuse the same chip for our CRC. And so the first thing I'm going to do is actually hook up a bunch of LEDs so we can see the contents of each of the D flip-flops. So basically what I'm going to do is I'm going to connect the outputs of each of these D flip-flops up to an LED, so the Q pin here, just so we can see, because each of these D flip-flops is going to store a bit, a 0 or a 1. And so by hooking an LED up to each one, we'll be able to see whether it's storing a 0 or a 1. Then I'm going to connect the other side of each of these LEDs to ground through a current limiting resistor. I think this is just a 270 ohm resistor, something like that. And as I'm hooking this up, it looks like some of these bits are on, but I guess I would expect just sort of random data in the D flip-flop. And so now I've connected the outputs for each of these 8 D flip-flops that are in this chip, but we're doing a 16-bit CRC, so we actually want another 8 bits here. So what I'm going to do is add a second 74HC273 chip over here and add another 8 LEDs. I can use a jumper here to connect my clear pin to ground momentarily, and that clears it. Okay, so we've got our 16D flip-flops here, and they're hooked up to LEDs so we can see what's in them. And we've even got our clock hooked up. That's this white wire that's hooked around here. And so now what we need to do is hook our data into one of them. I guess we'll do the one on the right here, just so everything kind of makes sense. And then hook the outputs of each one into the inputs of the next one. So that's what I'll do next, is just hook up all those outputs and inputs. Actually, before we do that, there is one thing we can test, which is just hooking the data into the first flip-flop and just verifying that that works. So I'll just disconnect the data signal here that we were using for the parity, and then I can connect a jumper from the data pin or the data out of the Arduino into the input for the first flip-flop over here. That should be there. So if I reset this, we should see the first one. Yeah, we see kind of some random stuff coming in here because I don't have the other inputs hooked in. They're floating. But this last LED, we should see pretty much following the data LED down here. And we see that. So if you ignore the other 15, there's just sort of reading in random floating garbage that's coming in. But this last one, yeah, it should be matching the data. So then what we need to do is then feed that into the one next to it. And so the output of, that was this one, is pin 19 into the input of the one next to it, which is pin 17. So let's hook pin 19 to pin 17. Now if I reset this, we should see those first two, and it does look like that, yeah, whatever goes into the first one, which comes from our data here, then gets fed into the next one on the next clock cycle. And again, ignore the last 14, because right now they're just garbage. So it looks like that's working, which is wonderful. So we can keep going, and basically I'm just going to connect the output of each flip-flop into the input of the one next to it. So at this point I've got the first 4, so let's just test that. And yep, it looks like in those first 4 we see data moving from right to left. So that looks good. So I'm going to keep going. So now the output of this guy's got to go down to the input of this. Okay, now I think I have the first 8 hooked up, so let's reset this and just see if those first 8, yeah, it looks like we're shifting along those first 8. So now I just need to connect into the second 8 over here. So I need to take the output of this LED and get it into the input for that one. So the output of that one, that's going to be pin 2 here. And then the input of the one next to it, that's this LED, comes all the way over here. So that's the top left again. That's going to be pin, let's see, pin 18. So pin 2 down here goes up to pin 18. And so now I'm basically going to do the same thing on this chip that I did over here, which is just wire all of the outputs of each flip-flop to the input of the next one. Okay, now I believe I've got it all hooked up. So what I can do is I can reset. So we've got all zeros in there. And now if I reset this, we should see our bits getting shifted in and shifted all the way across. And it should do that for the entire message. And so if we go back to that sort of slide and flip algorithm that we talked about before, we've got basically got the sliding figured out already. Now, the one thing we do need to change in the code for the transmitter is that once we've sent the message, we need to send an additional 16 zeros. As you'll remember, our original message, we had our message over here, and then we had 16 zeros that were then going to be filled in with the CRC. So if we go back to the code for our transmitter, this is our transmitter. One thing I'm going to change is I'm going to change the message to hi. And then if we go down to the bottom here, there's this little bit of code here where we're sending the parity bit. So I'm going to get rid of that because we aren't going to be sending the parity bit. Actually, yeah, I'll get rid of that. And then what we want to do after we send our data, so this is the loop where we send the data, we want to send those 16 zeros. So I'll just add a loop here. And basically in this loop, we just want to pulse the clock, which we actually have code for here. So we'll reuse that. And we want to send zeros, so let's make sure we... So let's see, what were we sending? TX data. So make sure our data is low. So we'll set our data low, and then we will send 16 clock pulses. And then we don't really need that parity stuff anymore. And so this should send 16 zeros. So just send hi. This is our message hi. And then we'll send the message down here, and then we'll set our data low, and then we'll pulse our clock from high to low 16 times. So that'll send 16 zeros. So I'm going to save this, make a new folder. This will be transmitter CRC. Call it transmitter CRC. So now let's program this. I'll hook the USB up and upload. All right, there it goes. It's sending hi, and now it's sending a bunch of zeros. So that looked like it worked, and we can reset it just to make sure, but there's our H, there's our I, there's our exclamation point going across, and then it just sends a bunch of zeros. So that's what we want. Because remember, that was originally what we had on this piece of paper here, because we had our message here, and then we had zeros over here, and then once we run it through our little algorithm, we'll get our CRC over there. Okay, so with our shift register, we've pretty much taken care of the sliding part of our sort of slide and flip mechanical CRC algorithm, but we still need to worry about the flipping part. So we're saying that once we start sliding this or shifting this data into our shift register here, once we get a 1 down here in this last place, we then want to be able to flip some of these other bits. And so normally when you think about flipping bits, you might think of using an inverter, and that certainly makes some sense. But we don't always want to invert the bits. We want to selectively invert them, or we want to invert them conditionally. And whenever you think about conditional inversion, the first thing that should come to your mind is an XOR gate. So if you look at the truth table for an XOR gate, what you'll see is that if you have one input, say the A input here is 0, then the output of the XOR gate is going to be the same as the B input. So whatever comes into B is what the XOR gate outputs. But if the A input is a 1, then whatever the XOR outputs is going to be the opposite of whatever the B input is. So anytime you think you might need a conditional inversion, XOR gate is definitely the first place you should look. And that's going to be useful because what we want to say is we want to invert the bits that are in these other positions whenever there's a 1 in this last position. Now the other thing you might have noticed is that our polynomial goes from x to the 16 down to 1, which is really x to the 0. So if you go from 0 to 16, then that gives you 17 places. And we've only got 16 flip-flops, so this doesn't quite seem to line up. So we're going to have to do something about that. But one thing that's sort of interesting about that is that if we look at this original thing that we did here before, we started out over here and we're feeding this through. And so yeah, we were looking at the span of 17 bits, but this last bit that we were flipping, this x to the 16 bit, the result of flipping that each time meant that all of the bits out here to the left ended up as all zeros. And then we ended up with the last 16 bits here being our CRC. Well, in a shift register, if this is our shift register, it's not really that important that we flip that last bit every time because we're basically tossing it out the end of our shift register and we're losing it anyway. So it doesn't really matter that we set it to 0. So you can kind of think of it as the bits we want to flip are the bits that are going into these 3 places. So we really don't need to flip that last bit because we're discarding it anyway. And then the other trick here is rather than thinking about, how do we flip what's in the register, what we can do is think about flipping the data as it enters the register. So if we just slide this over a little bit, this maybe changes the way we can think about this. So we can say if what's coming out of this last register is a 1, then what we want to do is when we do that shift, we want to flip the bit as it shifts from one register to the next. We want to flip that bit as it shifts from the one register to the next. Or here we want to flip the bit as we read it into the first register. And so that way we don't need to think about, how do we flip a bit in a register? And we don't have to think about, well, how do we handle this 17th place over here if we were to actually try to line it up like that. So lining it up this way helps us out a lot. And in fact, what we can do is just in those spots, if we insert an XOR gate, that'll let us invert that bit as it moves from one register to the next. So it's going to come out of this register, go through that XOR gate, and then whether it inverts it or not as it goes through that XOR gate will depend on this other input. And that other input comes from this last position over here. So if this last position is a 1, then we're going to invert the bit as it moves from this flip-flop to the next. We're going to invert this bit as it moves from this flip-flop to the next, and we're going to invert the new bit that's coming in. But if we have a 0 in our last register over here, then all of these XOR gates will just pass along whatever bit's being input into them. And so it'll work just like it did before. So now I think this new design here will not only do the shifting like we were doing before, but it'll also do the flipping when we need it to. And so hopefully if we just add these 3 XOR gates to our circuit, we'll be able to compute a CRC. So let's give it a try. Now conveniently, we've already got a 74HC86 over here, which is a quad XOR gate. So this is what that looks like. We've got 4 XOR gates in there. So I'll start by hooking in this first XOR gate all the way on the right here. So instead of our data going directly into our first D flip-flop, which is this yellow wire here, we'll go through an XOR gate. Okay, so our data now is going into pin 9 here, and then coming out pin 8. So we're going into one input of that XOR gate, coming out the output of the XOR gate, and back in to our initial data input. So then we'll need to connect pin 10, which is the second input of that XOR gate. We'll need to connect that around to our last D flip-flop here. And the output of that last D flip-flop is pin 2 over here. And so rather than connecting that directly up there, what I'm going to do is connect it to the other XOR gates. So I'll just sort of chain it around, because we're going to need that same signal to go to all 3 of the XOR gates that we're using. So I'll connect pin 2 to one of the inputs for the first XOR gate down there, and then I'll continue that around to one of the inputs for another XOR gate, and then I can bring it around to the top to an input for that third XOR gate, which is the one at the top that we were using before. So now we have our data coming out, it's going into this XOR gate at the top. The second input of that XOR gate is the last flip-flop here in our little string here. And then the output of that XOR gate is then going into the input over here. So now we've got this XOR gate here on the right hooked in. And we've also got these 2 pins of these 2 XOR gates wired up. So now we just need to insert these 2 XOR gates into the right place in our shift register. And so this one here is going to be after 1, 2, 3, 4, 5. So after the 5th. So between the 5th and 6th, we want to insert that XOR gate. And so we look over here. This is the first, so 1, 2, 3, 4, 5. So it's between this one and this one. So the output of this was going to be pin 9, and the input of the 6th one is going to be pin 7. So between pin 9 and pin 7, we should already have a jumper, and we do. That's this jumper here. So I'm going to pull that jumper out, and instead of a jumper, we're going to have to get that all the way over to one of these XOR gates. So the output there is going to go to the input over here, and so that's either pin 4 or pin 5. I'm already using pin 4, so pin 5 will be the other input. And so pin 4 and pin 5 are the inputs. The output is pin 6. So pin 6 is then got to come all the way back over to the right here. Pin 6 comes all the way back over here as an input to the next. Okay, so that should insert that XOR gate. So then we now need to insert this XOR gate, which is probably going to be easiest to count from this side. So 1, 2, 3, 4, and 5. So it's between the 4th and 5th from this side, which is actually just going to be, there's 4 on each side of this, so it's going to be this jumper that's jumping from one side to the other. So I pull that jumper out. And so now the output up here is going to come down into one of the inputs of our XOR gate. So pin 1 I'm already using, so we'll use pin 2 as the second input for that XOR gate. And then the output of that XOR gate will be pin 3. And so pin 3 then comes around to the input down here. And so now I've inserted that third XOR gate. So at this point, we should have this entire circuit built, which means that if we send our data, clock and data here, we should compute the CRC. So this is the moment of truth. And just to remind ourselves what that CRC is, here's what we computed before. So let me reset. And we should see data shifting. But when this gets to the end, we should see things not quite exactly shifting. And is that it? Is that right? That looks like it's right. 0011 000 11111101. Perfect. So we've computed the CRC completely in hardware. Okay, so now that we can compute the CRC, and we're doing that on the transmitter, we need to be able to compute the CRC on the receiver as well. So we need another circuit identical to what we have on the transmitter over on the receiver. So we need to build that now. Conveniently, I've already prepared one, and so this is identical to this. It should be exactly the same. And so I'll just go ahead and swap that in here in place of the parity circuit. And then I'll hook up the clock and data to a receiver. And actually, I just noticed one thing that I didn't do over here is I have the unused inputs for the 1 XOR gate that I'm not using. I just have those tied to ground. So let me do that on this one here too. Okay, now let's power up the receiver with the CRC circuit. And it looks like it's come up with some random stuff here, but we can reset that. So we've reset that, and I'll reset the transmitter as well. And now if I reset the transmitter, we should transmit the message. Oh, that's not working. What did I do wrong? Oh, do I have my clock and data plugged in the wrong place? I think I do. So let's see here. Data, clock is there. Data's there, I think. Let's reset and try again. There we go. And so we see the same thing on both. And we should see it compute the same CRC on both. So that gives us some assurance that what we received is the same as what we sent, because the CRC is the same. And in fact, if we wanted to test that, we can. If we reset here, and I'll just reset all these CRCs again. So now if we retransmit this again, and I'll inject an error this time. So now we have an error here, and we should see that we get a different CRC. And so, no surprise, our CRCs don't match. But of course, in reality, that's not how a CRC check works. You don't just compute the CRC on the transmitter, compute the CRC on the receiver, and look at both. Because, how does the receiver look at the CRC on the transmitter? The receiver is the thing that's validating the message, and all it has is the CRC that it's computed. So it has no way of knowing that it's different. So what we need to do is we need to transmit the CRC that's computed on the transmitter to the receiver so that the receiver can sort of do that comparison, if you will. And so we actually have to make a few changes here on the transmitter in order to do that. So if we look at what we've got right now, this is essentially a block diagram of our setup here. So we've got the Arduino on the one side with transmit clock and data, which are these two LEDs, going over to the receiver. And we have our receive clock and data over here. And those are connected across our transmission medium here. There's also a ground wire in here that I don't show in the diagrams, just so everything has a common ground reference point. But then the CRC computation on both is just sort of tapped in to the clock and data on both sides. And so, of course, if there's no errors, you'd expect to see the same CRC on both sides. But there's a couple problems with the way that this is set up right now. Because when we want to use a CRC, what we're doing is we're taking our message and we're adding these 16 zeros at the end of the message. And we do that so that when we compute the CRC, we can fill in those last 16 bits with the actual CRC. But in this case, what we're doing is we're sending our message, and then we're sending 16 zeros, and that's so we can get the 16 zeros into our CRC computation up here. But we're also at the same time sending those 16 zeros to the receiver. And we don't actually want to send zeros to the receiver. We want to send the CRC to the receiver. So what we need is we need some way to get the CRC out of this computation. So once we've computed it, we've got a CRC here, and that's great. But we need to get the CRC out of here and then transmit each of those bits across our transmission medium to the receiver somehow. And so that brings up two sort of questions, right? So one question is, how do we get data out of this CRC into our Arduino? So we need some way to get the data from the CRC computation back into the Arduino so that we can then transmit it across. And then the other question is, when we're sending those zeros in, how can we clock those zeros into the CRC computation without also sending them across to the receiver? Well, the way we can do that is add a couple extra control signals. So this is what I've come up with here. And so what I've done is separate the clock for the CRC computation on the transmitter to a separate CRC clock signal. So when we're sending our data, we'll put our data out here on the TX data line, and then we'll also pulse the TX clock to actually send the data across. But at the same time, we'll also pulse the CRC clock. And so that'll have the same effect as when our CRC, as it's configured now, the clock and data are connected directly to our transmission lines. So here we'll just pulse this TX clock and CRC clock at the same time, and that'll have the same effect. But then when we get to the end of our data, and we need to push those 16 zeros into our CRC computation thing in order to actually get the CRC, then we don't pulse the transmit clock. We just put a 0 out on our TX data, and we pulse the CRC clock 16 times, and that'll push 16 zeros in here. And then we'll actually have the CRC in our CRC computation, just like we do here, but we won't have sent those 16 zeros across to the receiver. So the next thing we need to do is we need to get the 16-bit CRC out of here and actually transmit the CRC to the receiver. And so for that, we have an output here. So with the output we can do, we can just read each bit out of here, and we can just keep pushing these bits along, read each one out into the Arduino, and then the Arduino can just pass that along to the transmit data and pulse that TX clock to send the 16 bits of the CRC over to the receiver here. So let's hook this up. So instead of our clock coming from our transmit clock here and going up to our CRC computation thing, what I'm going to do is remove that and hook this clock instead up to pin 13 of my Arduino. This is just a completely new, unused pin on the Arduino that I can use for the CRC clock. So now I've got this separate clock line. And then the other thing I want to do is I want to be able to get the output from the CRC computation and be able to feed that back into the Arduino. So I want to be able to pull data out of this thing and get it back into the Arduino. And so I want to take this last bit here, and that's connected to pin 2, and that's coming out of pin 2, I should say, and feed that into my Arduino. So I'll feed that into, where are we? Pin 10, I guess. And so what that's going to do is that's going to take the output of this shift register and feed that back into the Arduino. And that's our CRC output. And that way, to get the CRC out, we just need to shift all of those bits out and read them back into the Arduino. However, there is a little bit of a problem with this, which is that once we have a valid CRC in here, we want to be able to shift it out without modifying it. And the way this circuit is set up, we can't really do that because we've added these XOR gates. And so what's going to happen is as it's shifting out, if there's ever a 1 here, then these XOR gates are going to start inverting things, and that's going to mess up our CRC, and we aren't actually going to get the correct CRC out the other end. So to fix that, what we need to do is we need to have some way of sort of turning off these XOR gates to say that, hey, we just want to read what's in here. We don't want to do any of this inversion. And so we need a little bit of extra logic here to be able to sort of inhibit these XOR gates just while we're reading the CRC out. And since I don't really have any more room on the breadboards for any more logic, I came up with a little hack here with some diodes to do the logic. And effectively what I'm doing here is I'm just creating an AND gate with 2 diodes and a resistor. But just to walk through what's going on here, what we've got here in the normal case is if we're not just trying to do that read operation, if we're just doing the normal CRC computation, then this active low read thing will be high. It won't be active. So if this is high, and we've got this pulled high to 5 volts through a 100K resistor, then effectively this will normally be high right here. And because both sides of this diode are high, there's going to be no current flowing through that diode, this will just normally be high. And then if the output at the end here of our 16th flip-flop is high, then no current flows through this diode either, and this is still high. So if this is high, which is just how it worked when we had a wire, right? If this is high, this is high. But if what happens is the output of this goes low, then we have current flowing from our 5 volts through our resistor through this diode, because current can flow that way through the diode, and being sunk by this low output here. And in that case, because this is high and this is low on the other side of the diode only drops about 0.6 volts. So this side here will be just 0.6 volts, and that's low. And so now this will be low. So to summarize, if the output here goes low, then this side goes low as well, which again, same as if we just had the wire, right? This is low and it's low. So that's the normal case where this read line is high. But if we bring the read line low, then what that does is it creates a current flow this way through this diode, which means we're 5 volts here, we're at 0 volts here. The diode drops 0.6 volts or so. And so we'll have 0.6 volts here. So now this node will be low, and it will always be low. Even if this side goes high, because current can't flow this, from high to low through a diode that way. That's the wrong way. That's why we have a diode there. And so as long as our read line, as long as we pull that low, then this will always be low, which means that these XOR gates will always be inhibited. So this just gives us a control signal that we can use to sort of turn off the inverting operation of these XOR gates, regardless of what's going on here. But if the read line is high, then it works normally like we saw before. So what that means is that we're going to add that read line to our CRC thing, and we're going to have a CRC read signal on our Arduino. And of course, this will be connected just like that. So with that out of the way, let's go ahead and build our little diode resistor AND gate thing. So we're replacing this wire that goes from the output of the last flip-flop around to all of these XOR gates. So that's this wire right here. We'll kind of pull it halfway out. And I'll replace that wire actually with this first diode on the left. So that comes out and this diode goes in. Then this side of the diode we want to pull to 5 volts through a 100K resistor. So there's a resistor. And then we have another diode that goes to the read signal, which we're going to connect around to the Arduino somewhere. So let's see, I can put another diode in here. I'll just jump over to an unused part. And then the other side of that diode is there. And I can bring that down to my Arduino. And that'll go to pin, looks like D11 on the Arduino. There we go. Okay, so now we've got all of this stuff hooked up, which means that we now have the ability to control the clock to the CRC independently of the clock of our transmit clock. And it means that we can read the output of the CRC as well. So now we just need to update the code that's running on our Arduino to take advantage of all this. All right, so first what I'll do is I'll go ahead and define our additional pins here. So we don't have a parity pin anymore, but D10 is now the CRC output pin. So we just rename this CRC output. And then pin 11 is going to be that CRC read that we just built. And then the other pin we've got is pin 13 here, which is that second clock for the CRC. So that's CRC clock, that's pin 13. So those are our new signals. And let's see, we don't have parity anymore. We have CRC output, which is confusingly going to be input because it's output from the CRC computation, which will be input to the Arduino. Then we've got CRC read, which will be output. That's a control signal. The Arduino is going to tell the CRC computing thing that we want to read from it. And we have CRC clock, which is output, right? Because that's a clock signal going to the CRC computer thing. Okay, so we keep going here. Initialize our LCD, and here is where we are, is this where we're, yeah, this is where we're transmitting. And so we'll need to make one change here, which is when we pulse the clock, not only do we want to pulse the transmit clock, we also want to pulse the CRC clock. Because each data bit that we send, we want to send to both the receiver and to the CRC circuit. But then here, we're going to send our 16 zeros. And so when we send our 16 zeros, we don't want to pulse the transmit clock, we want to pulse the CRC clock. So this will send the 16 zeros now just to the CRC circuit. So at this point, let's actually give this a try and see if it's working so far. So let me plug in my USB and upload. I didn't reset anything, but let's reset our receiver here and reset our receive CRC. And now let's reset this. Now we see it's sending the data to both. And then at the end, oh, that's interesting. So it's sort of working. So there's a couple things going on here. So first off, what you'll see is that when it's sending the actual data, it's sending it to both. So you're seeing it go into this CRC circuit and you're seeing it going into this CRC circuit. But then when it finishes sending the data and it sends the 16 zeros, it's only sending them into the CRC circuit here. It's not actually sending them across our transmission medium. But what's interesting is that when it sends those 16 zeros in, it's just sending them in and it's not actually computing the CRC, and it's just filling it with zeros. And I believe that is probably because this read signal is probably telling it that we're in read mode, because I didn't actually do anything with that. And we probably need to set that high since it's active low. It's probably defaulting to low. And so everything we send in, it's not doing these XORs. And so it's just sending the data in and shifting it across. So let's look at the code and make sure we initialize that read signal high. So let's just go up to the top here. Yeah, I guess we can just do it here and make sure CRC read is high, which means that we're not reading, which means that it should compute a CRC. And I'll upload that. Okay, right off the bat, that looks better. But just to validate everything, let's reset and clear all of the things. And now if I reset this, what's going to happen is it's going to transmit the H, it's going to transmit the I, it's going to transmit the exclamation point. It is no longer transmitting anything, but it is filling the rest of this with zeros such that when it's done, we have the correct CRC, right? That's, if we double check our math here, that's the correct CRC in there. So at this point, we've sent the data and we've computed the CRC. Now we just need to send the CRC. And so to do that, what we need to do is toggle this into read mode and then read the output of the CRC as we pulse this clock, and then take that output and send it out the data to the receiver over here. So let's go down here. Here we send our 16 zeros. So just to back up here a second, here's we're going to send the data. We transmit the data. Then we fill the CRC circuit with 16 zeros. And now we need to read the CRC from the CRC circuit. So to read from the CRC circuit, first thing we need to do is put it into read mode. That way as we pull the data out, it's not going to keep doing those XORs or those inversions. And then we just want to go through 16 bits and read out the data. And actually what I'll do for now is just print the CRC on the screen. So I'll read it into the Arduino and print it on the screen. So let's and then what we can do is we can do lcd.print the CRC output. And then if that is high, we want to print a 1, otherwise we will print a 0. So that'll grab the leftmost bit out of the CRC circuit. And then what we want to do is shift everything in the CRC circuit left 1 so we can get the next bit. And to do that, we just need to pulse the CRC clock. So I'm just going to grab this code here, which does a delay. And then it pulses the CRC clock high, and then a delay, and then it pulses the CRC clock low. So that'll pulse the CRC clock. And then I think that's all we'll do. And what that should do is just go through and grab 16 bits out of the CRC and print them on the screen. So that should read in the CRC. So let's go ahead and upload that. And you can see it's reading something in there, but let's go ahead and reset everything. And we'll run this again. So now what it's going to do is it's going to send the H, it's going to send the I, it's going to send the exclamation, it's going to push 16 zeros into the CRC, and then it's going to read the contents of the CRC out. And so there we go. That is our CRC, and we can look here, and in fact that is the correct CRC. And so now the only thing left to do is to actually just transmit this CRC over to the receiver. And that should be simple enough, right? Because essentially what we just want to do is we want to take whatever we're reading from the CRC circuit and send it. So to send it, we're going to do a digital write for our TX data. And we want our transmit data to basically just be that same bit from our CRC. And then instead of, well, not instead of, but in addition to pulsing the CRC clock, we also want to pulse the transmit clock. So this is just going to be, take the transmit clock high and low. So read the CRC circuit, CRC from the CRC circuit, and so let's upload that. So I'll go ahead and reset everything. And at this point, now that we're actually computing and transmitting the entire message with the CRC, I want you to think about what's going to happen on the receiver here. Because at this point, what we're doing is we've got our message, we've computed our CRC, and we've added the CRC to the message. So what we're transmitting now is this entire polynomial. And the whole purpose of what we're doing here is that this polynomial will be divisible by our generator polynomial. So that means that if we compute the CRC of this transmitted polynomial, what is that CRC going to be? So in other words, this transmitted polynomial is computed to explicitly be divisible by our generator polynomial. So if we then, on the receiver, are dividing this by our generator polynomial, the remainder, that is the CRC, ought to be 0. So let's give it a try. So we're transmitting our H, we're transmitting our I, we're transmitting our exclamation, and we're feeding 16 zeros into the CRC circuit here. And now we're reading that CRC out and transmitting it. And when it's done, we've received the CRC here, and the computed CRC on the receiver is now 0. And that's actually how we validate that the message was received correctly, is because the receiver is going to receive the message plus these 2 extra bytes, which are the 16 bits of the CRC. So this 1 and this division symbol, that just happens to be what our CRC works out to be. And if we just ignore that part, we have our message, and then we have this extra bit that when we compute the CRC of that whole thing, the CRC is 0. And that 0 validates that we received the message correctly. And so if we're to reset everything and transmit, and this time inject an error, oops, I forgot to reset this side. Well, we'll let it go. I'll just reset that, clear this again. Okay, so now I'm going to retransmit here. This side's reset. Now if I inject an error, so we get some error in here, when we compute the CRC and send the CRC, we know we have an error because our final CRC on the receiver is not 0. So because this is not 0, we know that that is not our message. And so now at this point, of course, we can try this for any message we want. So we can change this back to a longer message, and it should compute the CRC for that. And if we want to verify that it's computing the CRC correctly, there's this website, crccalc.com, that will compute CRCs. And so we can put our message in here. So if we put in the message hi, so you calculate CRC 16, it comes up with a bunch of stuff here. And it has all these different algorithms. And so we have to find the algorithm that we're actually using. And one of the differences, of course, is the polynomial. And so you can see this polynomial, it puts it in hex. So hex 1021. If we convert that to binary, we get this. And that actually is the polynomial that we're using. So this would be the +1 term at the end. And then, this would be x squared, x to the third, x to the fourth, x to the fifth. So we have an x to the fifth term. And then this is x to the 12th. And of course, we also had x to the 16th, but that's not included here. And that's just because it's kind of assumed that if you're doing a 16-bit CRC, you're going to have an x to the 16th term. So they just kind of leave that out, since that way this just works out to be a 16-bit number. So the polynomial of 1021 is what we're looking for. But there's actually a couple different versions here that have a polynomial of 1021. So to figure out which of these we're actually doing, we can look at the result for hi. So when we do the math, or now that we have the circuit, when our circuit does the math, the CRC that we get is this, right? That's the same thing we got when we did our math. And so if we convert that to hex, we get 31FD. So we can go over here and we can see our result here, which one of these is 31FD. And actually it's all the way at the bottom, this last one here. So at least according to this website, the algorithm that we're using is CRC16X modem. And so you can see we have our polynomial of 1021. That's our polynomial. And then these other parameters, the reason that there's a couple things with 1021, even though they come up with different results, is there's a couple other parameters here. So one is init, and that is what the 16-bit shift register is initialized to before we start sending any data. So remember, we have to clear all the flip-flops before we start, so they're just filled with zeros. Well, we could fill it with something else. We could fill it with all ones, and that's what you're doing here. Or we could fill it with some other value. So there's a couple, there's different things you can do, but in our case, we're just filling it with all zeros. And then these last couple parameters are just some other things. So ref in means reflect in. So that says, are we going to reverse all of the bits in our message? And reflect out is, do we reverse all of the bits of our CRC after we've computed it? And then this XOR out, it says, do we take our CRC that we've computed and then XOR it by some hex value? And in our case, we're not reflecting it on the input. We're not reflecting on the output. We're not XORing it by anything. So that's why that's all false. We're initializing with 0, and then this is our polynomial. And so that's how we end up with this particular CRC. And now you might wonder, like, why would you do any of these things? Well, let me actually show you an example of why you might want to do something fancy like that. Let me reset all of this. And let's suppose that we have a problem with our communication here where the data is disconnected. So we're always going to receive zeros. So I'm going to permanently leave my disruption in the circuit there so that the clock is going to get through, but the data is not. Well, what happens with that is when I reset this, we send the H and all we receive is zeros. We send the I, all we receive is zeros. We send the exclamation, all we receive is zeros. We compute the CRC, we send the CRC, all we receive is zeros. And when we're done, our CRC check is all zeros, which means that we received it correctly. Well, obviously we didn't receive it correctly because there's no message over here. We just got a bunch of zeros. And so that's actually kind of an edge case where this particular implementation of CRC falls down. And so that's why doing something like initializing your CRC with some other weird value like this is going to catch a situation where you have a fault in your circuit where all you're receiving is zeros. So that's why you see some of these different things. And so, different little edge cases might benefit from different algorithms like this. But in any event, we know that what we've built is the CRC16X modem thing. So what we can do is we can plug in some other message like hello world, exclamation, and calculate that. And so this is supposedly the CRC for that. This is the CRC that we ought to compute. So let's go back here. We've got our message hello world, and I think I spelled that right. So let's go ahead and upload this. And as soon as it uploads, it's going to start transmitting. So I'm just going to let it run here. Oh, also, I still have my fault in here. So let me take that out and I'll just let it run. And now I'll reset everything. and go ahead and transmit hello world. And just like before, it's going to transmit each letter one at a time. And then when it's done, it's going to send the 16 zeros into the CRC computer on the left, and then it'll go ahead and transmit the CRC. And so now this is our CRC, and indeed it looks like that matched what we computed. And of course on our receiver, we've got a 0 there, so we know we received the message correctly. And of course, just like before, if we reset everything and transmit and inject any kind of error, it's pretty much impossible, or at least I have not been able to find a way to inject any kind of error here that isn't detected by the CRC. If I speed this up and let it run, very clearly detected that error. And so certainly just trying to inject errors by hand like this, it is pretty much impossible to fool it. Now, of course, if I had really good timing, maybe I could generate or inject an error that perfectly matches a multiple of our generator polynomial, and that would fool it. But that would be, very difficult to do. But it is possible. So someone that is maliciously trying to mess up your message could still do it with CRC, and that's why you get into things like cryptographic hashes and things where it's harder to intentionally inject an error that can't be detected. But with CRC, as I talked about in the last video where we went through the math, it's very difficult to have a random error that you won't be able to detect, and certainly, and it's difficult to have a burst error that you won't detect. Any kind of normal error that you would expect in a transmission network like this is extremely unlikely that you wouldn't detect. And so I think I'll leave things there for now. But one last thing that I'll point out that I think is kind of neat is that you may have noticed that there's some similarity between the circuit that we built for CRC and the circuit that we built for computing parity. Both use an XOR gate and D flip-flop. It's just that in the case of CRC, we've got a bunch of D flip-flops and we've got a number of XOR gates. And in the case of parity, we just have one of each. But if you look at just this first bit over here, the circuit's actually very similar. It's drawn a little bit differently there, but if we just kind of cut out the rest of these D flip-flops, this first part of our CRC circuit is actually, we can modify very, very simply to compute parity. And so you might be wondering, is there some deeper connection between CRC and parity? And in fact, there is, because this generator polynomial that we chose, we could have chosen a different polynomial. And by choosing a 16th degree polynomial, we get a 16-bit CRC. But if we'd chosen a 32 degree polynomial, we could have gotten a 32-bit CRC. Or if we'd chosen a first degree polynomial, we could get a 1-bit CRC. And in fact, in the last video, when I talked about how you might go about choosing a polynomial, I mentioned that in order to detect a single bit error, you need a polynomial that has at least 2 terms. For example, x plus 1. Well, x plus 1 is a first degree polynomial. And so if that is your generator polynomial, you're going to get a 1-bit CRC. And in fact, a 1-bit CRC, if you build the circuit for it, is going to look like this. Because you're going to have your x term, which is the output of this, and then you're going to have your plus 1 term, which is the XOR gate that's going back into the input. So the fact that our parity circuit and our CRC circuit look so similar is no coincidence.